This lecture is about stationary points for functions of several variables. If I have a function of one variable, such as f of x equal to x squared, then we can plot this function. The graph of this function, well, it looks something like this. The derivative of x squared is 2x, which is a linear function whose graph is something like this. For x equal to 0, the derivative is equal to 0, and so we say that 0 is a stationary point. Stationary points are useful when we try to find values of x which will minimize or maximize a function. But keep in mind that they are only candidates. In this particular example, x equal to 0 is the only stationary point, and it's also the minimum of the function. But for a function such as x to the 3, whose graph looks something like this, x equal to 0 is also a stationary point, but it's neither a minimum nor a maximum, not even locally. So in general, if f is a function from R to R, we say that x0, being a constant, is a stationary point of f if f prime x0 is equal to 0. Remember, f prime x is a function, and if x0 is a constant, this notation means that we are evaluating a function at the constant x0, and if that's 0, then this constant is called a stationary point. Another way of writing this is to write the derivative as df dx. That's a function. When you want to evaluate a derivative, we use this notation of this bar to the right. If I put x equal to x0, it means that I want to evaluate this derivative at the point x0, and if it's 0, then x0 is a stationary point. So let's move on to multivariate functions, and let's start with a simple example, the extension of x squared. So now f of x comma y is equal to x squared plus y squared, which is a simple quadratic form. We can make a graph of this function. It will be a three-dimensional graph because I have two x variables. So let's plot this in Wolfram Alpha. Just write plot x squared, which is x with a hat and square, plus y hat square, and press enter, and that will give us this nice plot of this function. The graph of this function looks like a bowl right here in the middle, where x is equal to 0 and y is equal to 0. The function takes the value 0, and we see that this particular point is the minimum of the function. This is not only a local but a global minimum of the function, which follows because x squared and y squared can never be negative. If we want to put this into matrix notation, we rename x to x1 and y to x2, and we write f of x equal to f of x1 comma x2 equal to x1 squared plus x2 squared. Then, since this is a function from R2 to R, the derivative is a 2 by 1 column vector, where in the first row we have the derivative of f with respect to x1, and that's 2x1, and then we have 2x2. The first one being the f, the x1, the second one being the f, the x2. So what do these numbers tell us? Well, the first one, df dx1, it tells us how the function responds to changing x1 when we keep x2 constant. That means that it will tell us the response of the function when I move in this direction. In the same way, the second element, df dx2, will tell us what happens to the function if I change x2 a little bit, or what happens to the function if I go in this direction. For example, for x0 being the 0 vector, f of x0 is equal to 0. This is the point at the bottom of the bowl. For this point, the derivative is the 0 vector. 2 times 0 is 0. And that tells me that if I begin at the bottom of the bowl and move just a tiny bit in the x1 direction, nothing happens to the function. Same thing if I move in the x2 direction. We can actually show that for a continuous function, if both the partial derivatives are 0, then the derivative in any direction will be 0. A tiny ant at the bottom of this bowl would consider herself to be on a slopeless surface. We call this point a stationary point. For this particular function, x1 squared plus x2 squared, we see that it's the only stationary point because this derivative, the f dx, is only 0 when both x1 and x2 is equal to 0. This means that we actually have the same definition of a stationary point for a multivariate function, namely the derivative of x evaluated at the point x0 should be equal to 0. The only difference is that this is a relationship between vectors. This, in general, is an m by 1 vector if f is a function of m variables, and this 0, well, that actually means a vector of zeros containing m of them. Each partial derivative must be 0 for this point to be stationary. To summarize this definition, if f is a function from Rm to R and we calculate the m by 1 vector of partial derivative df dx and we find a value of x called x0 which makes this vector into the 0 vector, that is every partial derivative is 0, then this constant x0 is called a stationary point of f. Just like for one variable functions, stationary points are candidates for min and max of the function. We also had this example of f of x being x1 squared plus x2 squared, where we found that x0 equal to 0 is the only stationary point, and this is also a global minimum of the function. x1 squared plus x2 squared is the simplest example of a quadratic form. So let's take a look at a general quadratic form, f of x being x transpose ax, where a is m by m and we assume that a is symmetric. We've seen before that the derivative of this function is given by 2 times a times x, which is m by 1. So if I want to find a stationary point of this function, I need to find a value of x, which makes this into the 0 vector. We can divide both sides by 2, and we're left with the balanced, homogeneous, linear system ax equal to 0. Since it's homogeneous, we know that x is equal to 0 must be a solution. Again, the 0 is a 0 vector. A quadratic form will always have a stationary point at the origin. The only question we have to ask ourselves then is this the only stationary point? Well, that translates into the question of whether there are other values of x which will solve this system. The answer to this question, well, that depends on whether a is invertible or not. If a is invertible, then we know that this is the only solution, because if a is invertible, I can multiply both sides by a inverse. These cancels, and I'm left with x, and the inverse of a times 0 is equal to 0, so that must be the only solution. But we also know from our study of linear systems that if A is not invertible, this particular system may actually have an infinite number of solutions. That is, you will find an infinite number of stationary points. We have already considered an example where A is invertible. Previously, we looked at the case where A was the identity matrix, which gave us f of x being x1 squared plus x2 squared. And then 0, 0 is the only stationary point. So let's take a look at a matrix which is not invertible, this one. The row echelon form of the augmented matrix is then given by 1, 1, 0, 0, 0, 0. Removing the 0 row and the final column, we see that the thing we're left with is not upper triangular, so A cannot be invertible. This particular A corresponds to the quadratic form f of x being x1 squared plus x2 squared plus 2x1 x2. So let's make a plot of this function. It's better to use x and y when we are dealing with Wolfram alpha. So in this case, we see that the function looks like this. This is very different from the bowl that we considered before. This is more like a sheet of paper where we have lifted these two corners. Along this diagonal here, we see that the function is 0 and that it's completely flat at each point along this line. So every point on this line is actually a stationary point. We can also see that by looking at the derivative. df dx is, with respect to x1, it's 2x1 plus 2x2. And with respect to x2, it's 2x2 plus 2x1. And there are many values which will make this the 0 vector. For example, 0, 0 will make it into 0, but also 1 minus 1 and minus 1, 1, and so on. Summarizing, we have the following important result. If we have a quadratic form, asymmetric and non-singular, then x equal to 0 is the only stationary point of this function. This is the corresponding result to the one variable case, where x equal to 0 is the only stationary point for the function f of x being equal to a non-zero constant times x squared. Let's consider another example, optimizing a multivariate quadratic function. A quadratic function of one variable can be written as f of x equal to ax squared plus bx plus c. And let's say that this is a proper quadratic function, so a is not 0. The derivative of this function is equal to 2ax plus b. To find the stationary point of this function, we set this equal to 0, and we solve for x, and we find that x is minus 1/2 a inverse times b. Normally we would of course write this as x equal to minus b over 2a. I use this form to demonstrate the similarities between the one variable case and the multivariate case. If f now is a function of m variables, then the corresponding quadratic function will be as follows. The first term, ax squared, will be replaced by a quadratic form, x transpose ax. The second term, the linear term bx, will be written as b transpose x, and then we have a constant c. So here, as before, x is m by 1, a is m by m, and b is m by 1. C is just a number. In the univariate case, we had to assume that a was different from 0, otherwise it wouldn't work. The corresponding assumption for the multivariate case is that we assume that a is invertible. as always, we also create a quadratic form such that a is symmetric. If I do the derivative of this function, I get 2 times a times x for the first part. Second, remember that the derivative of b prime x, that's just b without the transpose, and the derivative of the constant, that's just 0. F prime x is now a proper m×1 vector, which it needs to be. To find a stationary point, we have to find an x vector, which will make this derivative equal to 0. Moving b to the other side and dividing by 2, we have the following linear systems of equations. Since this is a balanced system and a is invertible, we know that the system has a unique solution, namely x equal to minus 1/2 a inverse times b. This result, it looks very much like the univariate result. The difference is of course that for the univariate result a and b are constants, while for the multivariate result a is a matrix and b is a vector. But this is the only stationary point of the function. Whether x is a minimum, maximum, or a saddle point will depend on the A matrix. If A is positive definite, then we know that this term is always greater than 0 except for x equal to 0, and we know that this term will go to plus infinity in all directions. This term can go to both plus and minus infinity, but since the first term contains the square of x, it will go to plus infinity much faster than anything that the second term can do. And so f of x will go to plus infinity when x goes to infinity in any direction, and that means that the stationary point must be a minimum. Similarly, if a is negative definite, then x must be a maximum.